In this video, we're going to work example problems involving the electron configurations of atoms. So let's get started. What is the Heisenberg uncertainty principle? What is the Schrödinger equation? So when quantum mechanics was being developed, as we've talked about in previous videos, you had Einstein answering the question regarding the photoelectric effect, where he postulated that to explain what was occurring, that electromagnetic radiation was composed of photons, these sort of light particles, but because light clearly exhibited at the same time wave properties in some circumstances, then you thought about light as having sort of this wave particle duality. Well, then de Broglie extended this concept and said, well, okay, we should be able to think about particles, things that are more conventionally thought of as particles. Light would be something you would more think of as inherently a wave, but something like an electron or a baseball you would think of more as a particle. Well, then those particles must exhibit that wave particle duality as well. And so that's where the whole idea of electrons, or really anything, having both wave and particle properties developed. Okay, but what was confusing about this was how can the position of a wave be specified? A wave extends in space. How can you specify the position of a wave? Well, this is one of the questions that the Heisenberg uncertainty principle helped people to wrap their brains around. The Heisenberg uncertainty principle also helped with these mind-bending experimental results that showed, if you looked at it, at the electron, and you saw it was a particle, but if you didn't measure it or look at it, it acted as a wave, right? What's going on? Well, the Heisenberg uncertainty principle just said that it's not possible to know both the momentum and the position of something with a certain degree of accuracy. And it gave the limitation on this with this inequality here. So this is position, this is momentum. You have Planck's constant and 4 pi. And so it suggested that maybe it's just the limitations of our senses that aren't allowing us to see what we're expecting to see. Now, I want to put an asterisk on what I just stated, because if quantum mechanics experts might say, well, no, it's not the limitations of our senses, that's literally what's happening. Even God wouldn't be able to. God designed it in a way to where, no, there's electrons are never in the same place at once. They are acting truly as waves and particles. So, okay, now the Schrödinger equation solved the problem of, there was a model of the electron configuration for hydrogen, the different orbitals that a hydrogen, the electron in a hydrogen atom could occupy, but there was no complete description for multi-electron atoms of the electron configuration. So Erwin Schrödinger used a complex mathematical technique to come up with an equation that describes not just the behavior of electrons surrounding atoms, but the behavior and energies of any submicroscopic particle for any circumstance. Schrödinger's equation is just famously known for being applied specifically for electron configurations, for mapping out electron configurations. But you can apply it to whatever you want. And what Schrödinger's equation does is it incorporates both particle and wave behavior, specifically with the wave behavior being associated with a probability density, the probability of finding an electron at a certain location. And if that's confusing to you, then this is made much clearer in the videos preceding this video in the playlist. How could a wave be associated with the probability of a particle at a certain location? This will make perfect sense if you go check out the previous video or 2 videos before this. So all you're doing with Schrödinger's equation is you are applying it to atoms, the electrons and atoms. You're solving for the wave function of each individual electron. Each individual electron is going to have its own wave function. But to solve Schrödinger's equation, you need to apply boundary conditions based on your specific problem, because it's not just about electrons, it's about whatever you want. That's what the quantum numbers are all about. Those are the boundary conditions to solve Schrödinger's equation. You apply boundary conditions for any given electron that you're wanting to solve for. Well, what are you wanting to solve for? You're wanting to solve for its probability density function, its its probable location at any point in space. That's what you're solving for. So for iron has 26 protons, neutrons, and electrons in its ground state. You're solving Schrodinger's equation for each one of those electrons to get what? What's the result? What do you get when you do this? You get its wave function, its probability density function, the probability of locating that electron at different points in space around the nucleus. And then with that, though, since you have it, it's like kind of like a position function in a sense. You can also get energies from that, velocities from that, etc. Energies of the electron. How is the concept of electron density used to describe the position of an electron in the quantum mechanical treatment of an atom? Yeah, so the parallel here is we learned about probability density in statistics, right? That's what they're talking about here. It's a probability density. Electron density is you're thinking about it's the probability density of that electron. It's the probability density based on the probability of finding that electron in a certain region of space. And it's the square of the wave function, the Schrodinger's wave function, gives you this electron density, this probability density. Describe the shapes of s, p, and d orbitals. How are these orbitals related to the quantum numbers n, l, and m sub l? Okay, so the s orbital is spherical, and well, technically orbitals don't have shapes, technically, because you could, if this is the nucleus of an atom, technically the probability functions, the wave functions extend as far as you want away from the atom, technically. But the way to describe these shapes, what they do is they say, okay, well, let's consider all of the regions where there's at least a 90% probability of finding the electron. There's a 90% chance of finding the electron somewhere within that region. If you go farther than that, yeah, technically the electron could be there, but if we just look at if we enclose the 90% region, then what does the shape of the wave function look like in that case? Okay, for an s orbital, when you do this, you enclose 90%, all regions where if you're within this boundary, there's a 90% chance that you're going to find the electron somewhere. That's going to be a sphere. Okay, the p orbital is going to be dumbbell shaped, like shown here, and the d orbital is kind of this double dumbbell shape, but then there's also for four of the five, but then there's one's going to be its own unique shape. Again, what this means is that within these regions, there's a 90% chance of finding the electron somewhere within these surface boundaries. Okay, now how are these orbitals related to the first three quantum numbers? So the principal quantum number n is giving you the size of the orbital. It has nothing to do with the shape. Like s orbitals with different n's, that's just telling you that the bigger the n, the bigger the orbital, or meaning the electron's going to spend more time on average farther away from the nucleus. All the n's going to tell you is if the n gets bigger for a p orbital, these just scale up in size. Same here. It doesn't change the shape at all. Only L changes the shape. L is telling you, is it a spherical s orbital? Is it a dumbbell shaped p orbital? Is it one of these shaped d orbitals, etc.? And then the m sub L is, so with an m sub L, you've already specified you're within a certain subshell. A subshell is a pairing of a principal quantum number and a angular momentum quantum number. So you know the size and you know the shape. M sub L is just telling you, well, which one of these orientations is the electron associated with? Right? You get the same size and shape orbital, but they can be oriented differently. So which one of these orientations is the electron associated with? That's what M sub L is telling you. Describe the four quantum numbers used to characterize an electron in an atom. So, okay, we just kind of went through this. N is the principal quantum number that tells you the size or the kind of the average amount of time that the electron spins away from the nucleus is further away, the larger the principal quantum number. It's just it's nothing to do with shape or orientation, just purely scale, size. Okay, the angular momentum quantum number is telling you shape. It is telling you the shape. Is it spherical? Is it dumbbell shaped, etc.? M sub L is just telling you, well, of those orbitals that have that same size and shape, there's ones that are oriented differently. Which one of those orientations are we talking about? Okay, and then M sub S is just telling you, okay, we're in the same subshell. We're in this one orbital that's oriented in this certain way. So now within that orbital, what's the spin of the electron? It's going to be either a spin in one direction or another direction. There's only two directions of spin. Okay, so that's why this is called the electron spin quantum number, and this is the magnetic quantum number. Which of the four quantum numbers determine A, the energy of an electron in a hydrogen atom and in a mini electron atom, B, the size of an orbital, C, the shape of an orbital, D, the orientation of an orbital in space? So part B is the easiest. The size of an orbital is determined by the principal quantum number, no matter what the circumstance. The bigger the n, the bigger the size of the orbital. Part A, it depends. If you're dealing with a single electron atom like hydrogen, then the energy of the electron is based on n. The bigger the n, the larger the energy. If you're dealing with a multi-electron atom, then the energy is based on both n and l. You have to look at n and l together. Okay, the shape of an orbital is purely based on L. The orientation of the orbital in space is based on M sub L. An electron in an atom is in the n equals 3 quantum level. List the possible values of L and M sub L that it can have. So the rule is this, okay? So you have n is equal to 3. All right, so now if n is equal to 3, then the possible values that the angular momentum quantum number can have, which is telling you the different shapes of orbitals you can have, is, so you take n and subtract 1 from it. So n minus 1 is 2. So what that means is, okay, so L can be 0, 1, or 2. That's what you do. You start at 0 and you count up integer values until you get to n minus 1. Okay, now M sub L, what you do with M sub L is you say, okay, you go to the largest value of L that you have. So in this case, it's 2. And all you're going to do is just list out, okay, since 2 is the largest value, then M sub L could be minus 2, 1, 0, 1, 2. There's 5 values of M sub L you could have. And you could get that value 5 from saying, okay, what's 2 times the largest L value plus 1? That's 5. And so that's going to match up here. But I find it easier just to remember, go to the largest value of L and just, okay, minus 2, 1, 0, 1, 2. If the largest value was 3, then this would be minus 3, minus 2, minus 1, 0, 1, 2, 3. There's 7 values here. 3 times 2 is 6, plus 1 is 7. Give the values of the 4 quantum numbers of an electron in the following orbitals. So if you have an electron in the 3s orbital, and these are really subshells. Subshells is any pairing of principal quantum number and angular momentum quantum number. So we know this is for part A, the electron is going to have its n is going to be 3 and its L is going to be 0 for sure. So we're in a subshell. We're in the 3s subshell. But okay, what about its magnetic quantum number? It's M sub L. Well, there's only one orientation of an s orbital. So this has to be 0. Okay, and so all that leaves is the electron spin quantum number can be plus or minus 1/2. Either plus 1/2 or minus 1/2, and you're still have an electron in this 3s orbital. Okay, part B, this has to be 4. This has to be 1, because it's a p orbital. L is going to be equal to 1. But now the magnetic quantum number can be, there's 3 differently oriented 4p orbitals, right? And then this could be plus or minus 1/2. You have 4, 1, pick any of these 3, pick any of these 2, and you have an electron in the 4p orbital. Okay, part C, 3, 2. This could be minus 2, minus 1, 0, 1, 2, plus or minus 1/2. any of these electrons would be in the 3D subshell. What is the difference between a 2px and a 2py orbital? Just the orientation. This is the same subshell, the 2-1 subshell, the 2p subshell. This is just telling you this could be -1, 0, or 1, and then plus or minus 1/2. These could be associated with any one of these three magnetic quantum numbers. And you might say, oh, well, no, it's X. This must be -1. Y, this must be 0. No, remember, we talked about there's no, that's beyond the scope of what we're talking about here in basic chemistry. The X, this could be associated with this magnetic quantum number. There's no rhyme or reason as far as which magnetic quantum number is associated with these different orientations. You know, this was, right, like shown here. It's not like, we know that the 3p orbitals are going to be perpendicular to one another, but as far as which one of these in which direction is associated with the -1, the 0, and the 1, we can't talk about that at the moment. That's beyond the scope of this course. List all the possible subshells and orbitals associated with the principal quantum number n is equal to 6. So, okay, let's go through this. N is equal to 6. L, then, we do 6 minus 1 is 5, so L can be 0, 1, 2, 3, 4, 5. That's in S, P, D, F, G, and I guess H would be next, orbital. Okay, the magnetic quantum number is, we go to the largest here, the largest L, and we do 2 times the largest L is 10, plus 1 is 11. So there's going to be 11 M sub L values. But what are the 11? Well, we just do this. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then M sub S, the electron spin, is plus or minus 1/2, always. Indicate the total number of p electrons in nitrogen, atomic number 7, s electrons in silicon, atomic number 14, and 3d electrons in sulfur, atomic number 16. All right, so if we come to the periodic table, it looks like, for these initial problems at least, they're not going to be giving us any elements that would have certain special cases that deviated from the normal pattern, right? When we get to, dealing with, potassium, calcium, some of these transition metals, then there's certain nuances, right? Here, we're just looking at nitrogen, silicon, and sulfur. Nitrogen, silicon, and sulfur. So we're not even dealing with the d orbitals. So, okay, what's the question? How many p electrons in nitrogen? Well, there's 3. Okay, so 3. What about s electrons in silicon? So, yeah, here we need to be careful because it's tempting to say, oh, well, there's just 2. But no, they're asking for total s electrons. So, like, even in nitrogen, there would be, 4 s electrons? You have 2s2 and 1s2. So in silicon, you've got 3s2, 2s2, and 1s2. There's 6 s electrons. Now, 3d electrons in sulfur, there's none. No, sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So there's none. Why do the 3s, 3p, and 3d orbitals have the same energy in a hydrogen atom, but different energies in a mini-electron atom? The reason is because with a hydrogen atom, all of those different orbitals exist. Those higher energy orbitals, they exist because you can have a hydrogen atom in its ground state, and then in that case, the electron's in the 1s orbital. But if it gets excited, electric current goes through it, it gets heated up, whatever, that electron can jump up to other orbitals. But no matter what, it's never having to interact with other electrons. So the only thing that dictates energy of the energy of that electron is its distance from the nucleus, its average distance from the nucleus. That's what the principal quantum numbers are all about. The 3 here is just telling you its distance from the nucleus. For a single electron hydrogen atom, that's it. That's the only criteria for energy. With multi-electron atoms, it's more than just its distance from the nucleus. That still is a big factor, but you also have to consider the shape of the orbitals. Differently shaped orbitals are more penetrating than other shaped orbitals. Penetrating meaning with multi-electron atoms, you have lower energy electrons are shielding the higher energy electrons, or I don't want to say energy, the electrons that are spaced less far from the nucleus than furtherly spaced out electrons are shielding those outer electrons from that stability of the nucleus. And differently shaped orbitals can penetrate that shielding better than other shaped orbitals. So that's why we talked about when it comes to with multi-electron atoms, when it comes to considering the energies of electrons, you have to take N and L together. N is still a big factor. It's not like it doesn't mean anything. No, it's a big factor. You're not going to have an N is equal to 5 electron in any circumstance have less energy than an N is equal to 3 electron, no matter what, because it's spaced too far out. However, in general, for multi-electron atoms, you have to take N and L together to determine the energy of the electron. Right? So why do the 3s, 3p, and 3d orbitals have the same energy in a hydrogen atom? Because the 3's are the same. That's all that matters. The average spacing from the nucleus. But in many electron atoms, well, no, because now that the L comes into play as well. Which orbital in each of the following pairs is lower in energy in a mini electron atom? So we learned the general rule that you can use to determine the energy order of, so as we just talked about, when it comes to energies of electrons and multi-electron atoms, you need to look at the N and L together, the subshell. If the subshells are the same, then it's going to have the same energy. So it's not like if you're in a 2p subshell that because, well, okay, you're going to have a different energy in the X-oriented subshell than the Y-oriented or the Z-oriented. No. Same subshell, same energy. Different subshell, different energy for a mini electron atom. So for a multi-electron atom, you make this chart. You say, okay, you do 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and you could keep going. 6s, 6p, 6d, and I'll start to condense it down. 7s, 7p, and you just, this is the order. You do this: 1s, 2s, 2p, 3s, 3p, 4s. Then you go 3d, 4p, 5s. You see, we went from 3p to 4s, then we went back down to the principal quantum number 3. 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. Now, but remember we talked about, though, this is to give you the general rule. In general, this is going to be the case. But it's not a hard and fast rule that you can apply to the entire periodic table. Whenever you get to different transition points, going from like a 3d to a 4s to a 3d or a 5s to a 4f, there can be some exceptions in those transition points, but in general, that's the pattern. So if we follow this pattern, then part A, 2s, 2p. 2s, 2p. So 2p is greater in energy than 2s. 3p, 3d. 3d is greater in energy than 3d. Or is that right? No, I'm not doing that right. Hold up. 1s, 2s, 2p. That's right. 3s, 3p, 3d. So 3d is greater in energy than 3p. 3s, 4s. 1s, 2s, 2p, 3s. Oh, wait, I'm screwing this up. Hold on. No. Wait up. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So 2p is greater in energy than 2s. 1s, 2s, 2p, 3s, yeah. 3p, 4s, then 3d. So 3d is greater in energy than 3p. Okay, now 3s and 4s Well, yeah, 4s is going to be greater in energy than 3s. Now, 4d and 5f. So did I get to 4d yet? So now we'll do 5s, 4d, 5p, 6s, 4f. So 4f. Oh, well, they said 5f. So definitely 5f is greater in energy. 4f is greater than energy than 4f, and 5f are greater than energy than 4d. But 4d is greater in energy than 5s. That's the tricky part. You think because of the 5, it would be less, it would be more energy than 4d, but that's not true. But 5f is definitely greater in energy than 4d. 4f is greater in energy than 4d. So definitely 5f. Explain the meaning of the symbol 4d6. So there's two ways of representing electron configurations, where electron configurations are just telling you how the electrons are distributed among the various atomic orbitals in an atom or element. Okay, one way is you have a big list of terms like this. And what this term is telling you is that it means that you have an orbital that's a D shape with principal quantum number 4. So the subshell is 4D. So in 4D, you've got, in any D subshell, no matter what the principal quantum number is, you're going to have 5 differently oriented orbitals. And it's just telling you, so that's a total of 10 possible electrons. And it's just telling you that of the 10 possible electrons in the 4D subshell, there's 6. And that's all it's telling you. So there's more information that you could be given here about, okay, well, how are those electrons distributed amongst the 5 D orbitals? But that's not telling you that here. It's just telling you that, look, there's in the 4D subshell, there's 6 electrons. That's what this is telling you. What is meant by the term shielding of electrons in an atom? Using the lithium atom as an example, describe the effect of shielding on the energy of electrons in an atom. Yeah, so for electrons, for stability, they want to interact with the nucleus. They want to interact with that positive charge for stability. So if there's other electrons in their way, and they would be in their way because they have a smaller principal quantum number, or perhaps since the shape is the shape of even though the principal quantum number is the same, since the shape of the orbital is different, maybe they have a better penetrating power of those lower quantum numbers. But the electrons with the lower quantum numbers are going to not allow the farther away electrons to interact with the nucleus. So they shield them from stability, is what this means. So with the lithium atom, lithium is 1s2, 2s1. The 1s2 electrons are shielding the 1s1 electron from the nucleus. That's why if you have a hydrogen atom, where in its ground state it's a 1s1 electron, but let's say that electron gets excited to the 2s orbital, well, that's going to have less energy than the 2s1 lithium electron because it's not shielded. The hydrogen electron that's been excited is not shielded like the lithium 2s electron is. The ground state electron configurations listed here are incorrect. Explain what mistakes have been made in each and write the correct electron configurations. So yeah, the ground state, remember that it's not like that you can't have excited states of these elements or atoms, but when we think about electron configurations, we're thinking about the most stable state is all. So okay, these are all incorrect. So why is this aluminum electron configuration incorrect? So we've got, let's see, aluminum. So 1s2, 2s2, 2p6. Okay, where's the 6 here? 3s2, 3p3. Yeah, I mean, they took 2 electrons from 2p and put them into 3p. No. So this should be 1s2, 2s2, 2p6, 3s2, 3p1. Okay, what about boron? Boron should be 1s2, 2s2, 2p1. Why is it 2p5? That's wrong. So 1s2, 2s2, 2p1. Okay, fluorine, you have 1s2, 2s2, and it should be 2p5. not 2p6. That's neon here. So it should be 1s2, 2s2, 2p5. Indicate the number of unpaired electrons present in each of the following atoms. Unpaired electrons. Okay. So we can also do electron configurations using orbital diagrams. So for boron, for example, we would have, so it's 1s2, 2s2, 2p1. So what we could do is we could draw it like this. 1s2, we could do that, and then 2s2, and then 2p, you've got, this is 2p1, and you do it like that. So here you can see that you have more information here. You can see how, and for the orbital diagram, you can see how the electrons are distributed amongst the orbitals. Here we can see the application of Hund's rule and the Pauli exclusion principle. If we did so for electron configuration 1s2, 2s2, 2p5, this is legitimate, but what if it wouldn't be legitimate if you put 3 of these electrons in the same orbital, right? That would violate the Pauli exclusion principle. We can't see details about that. Or we can't see details for just outline like this. We can't see details. Well, did you put so here we would be violating the Pauli exclusion principle. Here we would be violating Hund's rule, right? You want to have the all things being equal, you want to have the most number of parallel spins. We can't see if those principles are being violated here. We can with orbital diagrams. So, okay, with that then, let's see. So we've got boron has 1 unpaired electron. What about neon? That has none. Noble gases are everything's fully paired. Do we have any other noble gases? Oh, wait, no, none. Krypton, none. Okay, now let's see. Phosphorus is going to be, so 1s2, 2s2, 2p6, 3s2, 3p3. That's just going to be 1 unpaired electron. I'm trying to look for any special cases here. Let's see, what else? Is that scandium? Yeah, scandium's here. So yeah, this is one of those special cases. How did this work? Or maybe it wasn't. This is just, okay, argon, noble gas core, 4s2, and then 3d1. Was that it? I think it was. It was only when you got to, so it was argon gas core, 4s2, 3d1, 3d2, 3d3, and then you went for chromium, it transitioned to 4s1, 3d5 to have all those parallel spins. So yeah, scandium was just 4s2, 3d1. Manganese was 4s2, 1, 2, 3, 4, 5. Yeah, just there's no special case. This was 5 unpaired electrons. Right? We're applying Hund's rule here. We're saying you had the argon gas core and then 4s2 and then the 1, 2, 3, 5d5, you apply the electrons like this, right? 5 unpaired electrons. For scandium, it was 4s2, 5d1, 1 unpaired electron. Selenium is just argon gas core, 4s2, 5 or 3d10, and then 4p, 1, 2, 3, 4p4. But that means you're going to have, in the 4p4, you're going to have 1, 2, 3, so 2 unpaired electrons. Iron, you've got, where's iron? Here. So, okay, argon gas core, 4s2, 5 or 3d6, and there's no kind of special case here. You just do, yeah, what I did this was 3d. With 3d6, you just add an extra one. And so now you're left with 4 unpaired electrons. All right, CD should be cadmium. Okay, cadmium. Now, when we start getting far down the periodic table, we start getting into these crazy rules that we didn't really learn much about at the moment. But this should be, so 1, 2, 3, 4. It's 5s2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5d10. So there's no real transition issue here. It's just there's gonna be no unpaired electrons. It's only when you've got these unfilled orbitals that you can start then pulling from other orbitals to make parallel spins and whatnot is when you start getting these exceptions. Okay, iodine, there's gonna be one unpaired. Okay, lead, so yeah, I said there's one unpaired here because all of those rules, those exceptions, come into play when you're at transition points between D and F orbitals, or no, like S and D orbitals, or S and F orbitals, or D and P orbitals, when you're at those transitions. But once you get away from like the D and F orbitals, everything's pretty smooth. So like iodine, it's just going to be what is this? 2, 3, 4, a 5p5 with normal behavior. So this is 4p4, 5p5 is going to be like this, one unpaired. And then with lead, we're away from the 3, 4, the 5d. Here's 5d10. Now we're at 6p1, 6p2, so it's going to be normal. 6p2 is going to be like this, 2 unpaired. There we go. And actually, I don't know why I put 1. Phosphorus was 3. 3p3. Describe the characteristics of the following groups of elements: the transition metals, the lanthanides, and the actinides. Okay. So the transition metals are in this center region here, and what makes them transition metals is in their ground state, elemental state, they contain incompletely filled d orbitals, or they give rise to cations that have incompletely filled d orbitals. Either case, if they're associated from either a ground state perspective or like a bonding perspective with incompletely filled d orbitals, then that's what you think about as a transition metal. Lanthanides and actinides is the exact same concept, except with lanthanides, the orbitals that are not completely filled is the 4f. With transition metals, it's any d orbital with any principal quantum number. With the lanthanides, it's specifically the 4f's. With the actinides, it's specifically the 5f's. And so here's the lanthanides and here's the actinides. What are the group and period of the element osmium? All right. So here's osmium. Now, the group is the column. So group 8, or Roman numeral 8. But this also, with the group name, it gives a B, but I have another periodic table that I'm looking at printed out that doesn't indicate the B. It only has the number 8 and Roman numeral 8. So group 8, and then the period is the row. So 1, 2, 3, 4, 5, 6, period 6. Explain why the ground state electron configurations of chromium and copper are different from what we might expect. Yeah, so this is where the special cases come in, and what happens is, because when you have these, so the 4s is a little bit less energy than 3d because of the shielding effect and the penetrating power of the differently shaped orbitals, but they're still really close in energy, 4s and 3d. So what you can think about is what happens is, because they're close in energy, Hund's rule can potentially overpower that gap in energy. And it does in the case of that. When you typically would just go from argon gas core to 4s2 to, then it would be 1, 2, 3, then yeah, that would be 3d4, right? So then you would have 1, 2, 3, 4, 1, 2, 3, 4, and that would be it. But it's more favorable to, in this case, to take one of these electrons from 4s2 and put it out here to get all these parallel spins. And so that's exactly what happens. But the only reason this can take place is because the 4s and the 3d subshells are close enough in energy. This doesn't take place in general. Okay, now copper is, this is a little bit different than what we just talked about, because what happens with copper is you get, so you would think it would be argon gas core, 4s2, and then 3d9. But instead what happens is you get argon gas core, 4s1, 3d10. And the reason why this happens is because it's more energetically favorable, and this only can take place because these subshells are close enough in energy to begin with. It's more energetically favorable to have an entire subshell with unpaired electrons, and then another entire subshell with all paired electrons, as opposed to having an entire subshell with paired electrons, the 4s2, and then an incompletely filled or non-all parallel subshell. Comment on the correctness of the following statement. The probability of finding 2 electrons with the same 4 quantum numbers in an atom is 0. True. This is based on the Pauli exclusion principle. It's one of the foundational rules that we use to build electron configurations, to map out the locations of electrons around an atom. It is not possible to have 2 electrons with the exact same 4 quantum numbers. Use the Aufbau principle to obtain the ground state electron configuration of technetium. Okay, so the Aufbau principle was just that building up principle where you can put, a noble gas core and then you just go step by step using the Pauli exclusion principle, the energy level principle, and Hund's rule, etc., to build up the configuration, electron by electron. So, okay, technetium is here in 4D. Okay, so we'll have a krypton noble gas core. Let's do this. So krypton noble gas core, then let's see. So conventionally, with no special rules, we would have 5s2 and then 1, 2, 3, 4, and then 4d5. So, and then that would be 1, 2, 3, 4, 5. Is that right? Krypton core, 5s2, 1, 2, 3, 4, 5. Okay, using the traditional conventional rules, this is what the ground state electron configuration would be. And it looks like this is probably going to be correct because there's no, it's those special cases only come into play to where if we had like an empty orbital here. Okay, well then do we pull this one out? Right? If this was empty, then do we take this electron from here and bring it over here to make all these have parallel spins? But that's not an issue here. This is everything we talked about. We've got a fully, this is going to be correct. We have a full orbital that's all paired, a full orbital that's all parallel spins. So this is it. This is it. 5s2, 4d5, krypton noble gas core. This, based on everything we talked about, Pauli exclusion principle, Hund's rule, the everything, we didn't learn how to deal with all exceptions across the board, but everything we were taught in the textbook, this lines up perfectly with. Okay, write the ground state electron configurations for the following elements, okay? So let's start with germanium. So the argon noble gas core, okay, then we'll have 4s2, 3d10, and now we're away from any of these transition points with the S's and the D's and the F's or anything. We're just now into 4p2. All right. What about iron? Iron, we've got, where's iron? Here. So argon core. Now, okay. 4s2 and then 1, 2, 3, 4, 5, 6. So, okay. This should be, we learned about the exceptions when it came to the 3D subshell. We didn't go into too much detail about the different exceptions that come into play with 4D and 4F and whatnot, but with the 3D subshell, we learned all the exceptions. The exceptions were based on the chromium and the copper, but there was no other exceptions. So this is just going to be 4s2, 5d6, and you just fill it up as normal. 4s2 is filled up, and the 5ds, you're going to have 4 parallel spins, 1 paired spin. Okay, let's see. Zinc, you would have, where is zinc? Here. Well, this is right on the edge here. This is 3d10. So zinc, you're going to have the argon gas core, 4s2, 3d10. That's it. 4s2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The only exceptions that we learned about was with this 3D subshell was copper and chromium. But when we get into the 4D, the 4F, the 5F, and whatnot, there was a lot more going on. So, okay. Nickel, where is nickel? Okay, this is not one of the exceptions. This is going to be argon gas core, 4s2, and then 3d8. Everything filled up like normal. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. Okay, W is what? Tungsten. So, okay, now here we get into some weird stuff going on. So unless we're far removed from a transition point, then we're not going to know how to deal with this. So let's check it out. We have a xenon noble gas core. Now, traditionally, we would just say, okay, let's see, 1, 2, 3, 4, 5, 6s2, and then 4f14, and then what? 1, 2, 3, 4, 5d4. If there was no exceptions, this is what we would write for the electron configuration. But, okay, the 5d4, I mean, yeah, that's an incompletely filled D subshell, but we could do like 1, 2, 3, 4, 1, 2, 3, 4. We could pull maybe from the 6s or the 4f, pull an electron to make a full unparalleled spin orbital. But I don't know. That seems like a stretch having to pull from the 6s or the 4f. But let's see what the textbook says about tungsten. Okay, so this is the electron configuration for tungsten. We're far enough removed from the transition points to where we've returned back to normal behavior, the conventional behavior based on that diagonal chart, and just applying the energy levels based on this chart, the Pauli exclusion principle, and Hund's rule like normal. Once we're away from the boundaries, it all returns back to that traditional way. It's only when you're at the boundaries where you start getting these exceptions. Okay, TL is thallium, so that's here. So xenon noble gas core, then 6s2, 4f14, 5d10, and then we just move on with 6p. Usually transitioning to p is pretty straightforward. 6p1. In other words, we don't start pulling electrons from d orbitals or f orbitals into p orbitals. We're only doing that between s orbitals and d orbitals, and f and d potentially. So this should be correct. Let me check. Yeah, that's right. Which of the following species has the most unpaired electrons? So this sulfur here, there's sulfur cation, anion, and just sulfur element. So, okay, let's write the electron configuration of sulfur. So we've got a neon noble gas core. Then we've got 3s2. Let's do this. Neon noble gas core, 3s2. Then 3p4. So okay. Which of the following species has the most unpaired electrons? So this one has 2, we can see. S plus, we remove an electron, so now we have 3 unpaired. S minus, we add an electron, so now we only have 1. So we can think about, as far as ions, the electrons that are going to be removed are going to be the outermost highest energy electrons. So they're going to be, in this case, they're going to be coming from this 3p orbital. So if we consider that, then there's 2 unpaired electrons here. With the cation, we remove an electron. There's 3. Anion, there's only 1 because we added an electron.